Okay, off we go. Lots to do today. I'm sure you all have noticed. Today is our last, regular class meeting of the semester. It's weird. It feels like the semester just got started. But anyway, so lots to do. We're going to finish up with chapter 7. Actually, pretty soon. There's some supplemental examples that I like to be able to do when I can, when time permits. We are a little tight on time, so I'm going to have to kind of hustle through those examples. But I think we'll be able to do all that's the most important things about those examples is what I'm going to call the diagnosis aspect. How to figure out what the right method is to solve the problem, not the actual solving of the problem. Then after that, we're going to get into chapter 4 a little bit. We're going to finish chapter 4 after the exam on next week, whenever that is, Tuesday, I guess. And another thing that has snuck up on me, I guess I better start writing that exam. And then we will finish up chapter 4. Okay. All right. Okay. So last time we were talking about surface independence. This is a really cool idea. It's very computationally powerful. The big idea is that it's a lot like path independence, just kind of one dimension up. And I like to go over to the diagram and be explicit about that. Let's see here. I'll go into this mode. This little, what I like to call diagram chase, borrowing a phrase, is representing path independence, and surface independence, really, literally, it's the same thing, just, one dimension to the right? Everything goes up by one dimension. So we have these special vector fields that are surface independent. We don't look at curves with the same boundary points. We look at surfaces with the same boundary curves. So everything's one dimension up. And then, by the way, what do they relate to? Well, what we saw last time, and let me leave this about like so, I suppose. Oh, and did I? I'll leave that there. Last time what we saw is that analogous to what we saw with path independence. Actually, you know what? Let me bring this back a notch here. In path independence, we connected being a gradient to being path independent by using the fundamental theorem of line integrals. The pattern, then, and this is not mathematical reasoning, this is pure strategic speculation, but the diagram would seem to suggest then that if I want to connect being a curl with being surface independent, maybe Stokes' theorem would be the tool that would allow us to draw that conclusion, and that's what we saw last time. So this was what we ended with last time. We showed that Stokes' theorem, is the thing. That's what allows you to compute these two fluxes with their corresponding boundary line integrals, and of course, if they have the same boundary, and from that you conclude you get the same fluxes. That is what surface independence is, So Stokes' theorem did, as the diagram, you might say, as the diagram predicted, Stokes' theorem is the thing that makes that work. So we're going to see another example of kind of that same sort of thing happening real quick here. What did I just do? Okay, here we go. So looking back, I guess I'd better get this out of the way. Looking back, when we were talking about path independence, another thing that we did is we showed that path-independent vector fields have curl equal to 0. Regularity issues aside, again, I don't want to get bogged down in difficult. So path-independent vector fields have curl equal to 0, and vice versa. And how did we do that? Well, we used Stokes' theorem. We did that last time. Stokes' theorem was we had to wait until we had Stokes' theorem. We did something analogous with Green's theorem, a couple of weeks ago, But we had to wait till we had Stokes' theorem, and in fact, it was the missing piece. It was the thing that allowed us to make this connection. So again, now speculating, hopefully, maybe, possibly, the diagram would seem to suggest the way we would connect surface independence with divergence being 0. Maybe, which, by the way, wouldn't that be cool? The way we might hope for that to be true and the way we might show that to be true, perhaps Gauss's divergence theorem. It's kind of what the diagram's sort of suggesting. So let's see if that works. And in fact, it totally does. And as y'all have long since noticed, I'm sure, when arguments or constructions or what have you are analogous to things we've seen previously, I like to lay it out on the page the same way to emphasize the analogy. And it's pretty strong. We have previously seen that being a curl is equivalent to surface independence. Again, regularity issues assumed, ignored. Being a curl is surface independence. Surface independence is about closed boundary fluxes being 0. All of this we saw last time. And now, as predicted, here it is, Gauss's theorem. Gauss's theorem, which tells us that closed boundary fluxes are triple integrals of divergence in the interior, right, is the thing that makes that equation turn into that equation, and then I can make an analogous argument to what we did before. Wait a minute, you're telling me that divergence is this thing where no matter what you integrate it over, you always get 0? Really? Over every domain? No matter what solid you integrate this thing, you always get 0? What could it possibly be? It itself must be 0. So, super analogous, right, to what we saw. And again, as predicted, Gauss's theorem is the thing that makes it work. So, very cool. Keep in mind, part of my goal here, I have multiple goals in showing you this stuff. One of my goals is to make sure you know certain facts that you need to know. Right? Another thing is I want you to understand mathematical reasoning. Again, that's what we're here for. That's really the most important thing in all of this. But I have this other goal with all of what we're doing at this point. And what basically the big focus of today is going to be, how is the diagram helpful to you? Right? And what I claim we got out of this was possibly a little bit better understanding of how surface independence and path independence are very strongly connected, very closely analogous in how the diagram predicts which theorems and how are going to be useful in learning about surface independence, just like they were with path independence. So I'm going to be making a lot of use of this diagram today. Again, my big one of my big goals for today is to make sure you see how useful this diagram is to you. And we'll come back and hit that again in a few minutes. Okay, so let's see an example. By the way, we do have now our nice local test. If you have a vector field and you want to know, is that vector field surface independent? Useful, very useful property to have, by the way. Pretty awesome when you know a vector field is surface independent. It means you get to change the surface almost to whatever you want. It's almost too good to be true, right? It's amazing property. Very computationally useful, and we can test for it with this handy dandy local test, which is just compute the divergence and see if you get 0. Easy to do, right? Easy test, powerful conclusion, right? Totally awesome. Okay, so with that in mind, let's do one. Here's the example. I've remarked on this before. Let me do it again. Notice that in the statement of the question here, there is no suggestion of how you should compute the thing that they're asking you to compute. Right? And that's why I go with this toolbox full of tools metaphor. You got to familiarize yourself with these tools, kind of get the hang of what they're good at, what they're not good at, and decide for yourself which tool to use. All right, so one thing you could do, you could parameterize that surface. It's not even all that bad. From the parameterization, you could take the partials, do the cross product, compute the capital N vector, and play that whole game, pull back through the parameterization. I mean, you can do all that, right? It is a fair amount of legwork. And by the way, it is only doable because I didn't feel it necessary to go to the trouble to make it undoable. Right? There are plenty of examples where the plug and chug method just wouldn't work very well. Right? But I didn't want to make this, uglier than it needed to be. Okay, so plug and chug, I suppose an option. Let's consider our options, though. We're computing a flux. By the way, this will be a little bit of a preview of the big examples we're going to do. We are in three-dimensional space, and we've been asked to compute a flux. And right off the bat, since this is what we've been asked to compute, right off the bat, we know a couple of things. We know these are our candidate theorems in terms of these accumulation theorems. Like, this is where we're at. And so, related note, there is no way that the fundamental theorem of line integrals is going to be relevant on this. Right? So don't waste your time thinking about that. Right? It's no chance. It's not even connected to flux integrals. So don't bother. So we have a vector field given to us, and I claim the diagram helps us out very naturally, very nicely. And I encourage you to take the help when it's given, right? The diagram is giving us help here. The diagram is telling us what to do. The diagram is telling us, hey, here's what you should do. Whenever you have a vector field in that spot, you should compute the divergence and see what you get. Because it might be useful. And it might be useful in a couple of different ways even, right? So let's do that. By the way, one obvious use, depending on what you compute, depending on what you get, that would end up being the integrand in a possible application of Gauss's divergence theorem. So there's one possible use right there, right? There's going to be another one momentarily. So we take our vector field. We compute the divergence because the diagram told us to. We get 0, and then we know a couple of things. One thing, going back to the diagram, what happens when you're looking at you got a thing here, and you compute and you get 0, and you remember everything has a lifetime of 2, right? And what that tells you is there is some other vector field. I don't know what it is, but there is some other vector field out there whose curl is the original vector field you were given. Your given vector field has an anti-curl. That's immediate conclusion from having computed the divergence is 0. Now, bad news, we don't know how to compute anti-curls. So it's not clear how you're going to make use of this information in this example. Nevertheless, that is a conclusion. The other thing, what is going to be useful here, here it is. We just computed the local test. We computed divergence. We got 0, and therefore we conclude our vector field is surface independence. Has surface independence. How we doing? Everybody on board? Okay. Alrighty. Cool. Surface independent. Well, that's a tremendously useful piece of information. Knowing that it's surface independent. Let's see here. So I was initially given this surface, which I can draw about like this. By the way, make sure you can do this. This, of course, is a stretched out, well, it's an elliptical paraboloid, right? So you can think of this as a parabola that's been rotated, but then subsequently also stretched or squished. Take your pick. So we know that looks approximately like this. Make sure you can do that. We are, of course, only looking at the part where z is greater than or equal to 0, so just the part that's above the xy plane, like so, and that's why we stop it there. So that's what our surface is. Now let me address a difficult matter that a lot of students get stung on. This is a nasty little landmine. Please don't step on the following landmine. A lot of students will draw perfectly reasonably like this, and then they will perfectly reasonably draw the, sort of the edge that gets made when you make that cut. And then they look at their own picture, and very understandably they get confused and think that what they have drawn includes both all of this stuff up here and this down here, and it does not. This stuff down here is not part of our surface. When you look at the phrasing of the example, it says S is part of that paraboloid. What I have X'd out in red there is not part of the paraboloid. It was never on the surface in the first place. And this subsequent clarification of, well, this is specifically the part of the paraboloid I'm interested in, doesn't change the fact that that gray region that I've got there, it never was part of the paraboloid in the first place. So it's not included. This is not a closed surface. S is not a closed surface. S is just this part up here. It's an upside down cereal bowl. And the cereal falls out. Everybody clear on what this surface looks like? By the way, here's why that's so important, right? If you misunderstand what this surface is, if you mistakenly allow yourself to think that the surface includes all of this down here also, in addition to all of this up here, you would be mistakenly under the impression this is a closed surface. You would be mistakenly under the impression that you can apply the divergence theorem. And you would get a completely wrong answer. Correction, your solution would not be mathematically valid in any sense. You would coincidentally get the right number at the bottom. But again, fortunate coincidences don't count, right? Excuse me, we're interested in valid mathematical reasoning, and if you totally misunderstand the surface, and apply properties that don't apply to the actual surface. And again, you're off in left field and it doesn't make any sense. Does everybody see why this is so dangerous? Right, so be very, very careful, please, when you're interpreting the question. That is part of the problem, is to correctly interpret what is the question asking. So careful, careful. Okay, so we've got a surface. We know our surface is we know our vector field is surface independent. Surface independent says whatever surface I've been asked to compute the flux of, I mean, just make sure you don't change the boundary, fix that boundary, and with that understanding that you can't change the boundary, pick any other surface you want. Compute that flux. It's gonna be the same if you know your vector field is surface independent. Again, kind of unbelievable. Wait, you gotta be kidding me. I get to pick any surface I want. That's crazy. Okay, so there's a pretty natural choice here. Our surface looks like this. The boundary looks like that. Now, think creatively. What's your favorite surface that has that same purple boundary? I have a personal favorite. It's the nice, easy, flat one right there. Exactly the part that we had to, go to some pains to make sure was clear and not part of the original surface. Conveniently, yeah, but it does have the exact same boundary. So what I can do then is I can say phooey on this green surface. It's all curvy and stuff, and annoying, right? That seems like it's going to be inconvenient. No problem. Surface independence tells me I can look at this blue surface here instead. Phooey on the green surface. I don't even need to think about the boundary anymore. I've already translated to this blue flux, and now I've got a totally different question. Compute the flux through this blue surface. And that's actually pretty easy. It's pretty straightforward to write down the normal vector. After all, it is perfectly horizontal. Yes?
About the normal vector?
Yeah.
Down because it says it's oriented down?
No, it's a great question. I'm totally coming back to that. Yeah, no, that's quite all right, but great question. I will come back. Point being, the normal vector is pretty easy to write down. Yes, we'll cover the orientation in a second. That makes this dot product really easy to write down because the original vector field, the original vector field was that. Real easy dot product, real easy resulting integral, a scalar surface integral no less. Scalar surface integrals open up, again, more options for how to compute. Scalar surface integrals, we can make odd symmetry arguments. Look how convenient our integrand is. And you have a couple of options even on how to make the odd symmetry argument. And do make sure to think those through, by the way. But this is equal to 0 by symmetry, but make sure you're clear on what plane you're using. Again, that's a requirement. If you want credit for a symmetry argument, you have to say it's equal to 0. You have to say you're using a symmetry argument, and you have to say through what plane are you are you claiming that there is a symmetry argument? Oh, and you have to be right. Right? Okay. All right. Okay. So, powerful conclusion. I'm coming back to the orientation in a moment. But we didn't have to parameterize anything. We turned a inconvenient plug and chug into a couple of clever observations and almost no algebra. Right? This is very desirable, very nice solution. Okay, what's the deal? Oh, yeah, question.
Is it a scalar surface integral? Because yes, isn't it?
Yeah, this is a scalar surface integral because this is because the orientation has been sort of dealt with. Is sort of the easiest way to say it. I mean, yes, this is a scalar, and this doesn't have any orientation dependence. It's just a scalar valued function on us with a scalar differential. Yeah. Right. Okay. What's the deal with the orientation? So it is tempting to say that downward means that, and that is not valid reasoning because downward refers to the original S. That merely tells us that this was downward, right? And so it does not follow that, whatever, casual description we may have given to the original surface will also apply in a casual sense to the new surface that we pull out of thin air. It just doesn't work that way. So what we have to do is play with swirls, and this is just a matter of doing it, and you got to think three-dimensionally, and there's just kind of no way around that. Let's see if I can, there we go. So our given orientation is downward, which you'll see is kind of sort of, you're going to want to call that inward loosely, and that's kind of okay. Right hand, thumb, fingers create a swirl. You think about how that swirl, how does that swirl sideswipe? If you imagine these swirls kind of approaching down here like that, how does that sideswipe up against our boundary? And it sideswipes like so. All right, now there's a lot of, geometric visualizing to make sure that you can do. Give yourself the time, think it through. But so that's our boundary orientation. Now, when it comes time to think about the new surface, I made a bad color choice there. Let me do purple. Now, thinking about our new surface, we decided we wanted to use this surface. How do we orient it? And remember the rule. The rule is your new surface has to have the same boundary as your old surface. Same means it's got to be not only the same curve, but it has to be oriented the same as well. So I've got to look at my options here, right? I have two contenders, you might say, for, I didn't mean I wanted the pencil. I've got two contenders for how to orient. I could orient upward. I could orient downward. Which one's the right one? And you just consider both options and play the game. And pretty quick pitch, I think. If you were to orient upward, fingers of your right hand goes the wrong way. If you orient, on the other hand, downward, thumb pointing downward, fingers of your right hand, and it goes the correct direction. So downward. Happy little coincidence that it's described casually by the same casual terminology. I wouldn't go so far as to say it's 100% coincidence, but it's certainly not something that you can conclude for free. Everybody happy with this? Okay. All right. Okay. So, moving along. Okay, so we are, whoopsie, wrong button. Oh gosh. We are kind of done with chapter 7 in some sense. I do like to remind you all of the diagram. This whole page here is just hey, don't forget, diagram's pretty cool. Lots of patterns, lots of uses, and we've already talked through a lot of that, right? So we talked about how we've got these three properties of the special vector fields that they come from over here. When you go further, you get 0. And they have this independence that if you change the domain without changing the boundary, you'll always get the same value of the integral. And that works for path independence and surface independence. Right, so that's kind of a cool pattern, the fact that this sort of, maintains, here or here, either one. Think of it this way, this cuts in half the number of things you need to memorize. You don't need to memorize that, these three properties are connected, and separately, independently, that these three properties are connected, right? That's sort of 6 properties to keep track of. All you need to keep track of is one pattern. That this pattern holds kind of wherever. Take your pick. Right? So it's, this is a very convenient, pedagogical, shortcut to help you keep track of things. Likewise, how many of these accumulation theorems do you need to memorize? Arguably none, in the sense that they all have the same pattern. Just understand the pattern. And whether you're talking about line integrals and antigradients or fluxes and curls and divergence and oh my gosh, whatever, right? In all cases, you apply the operator, you take the boundary, sort of correspondingly, and this computation and that computation will always give you the same thing. One pattern. And it applies, it applies for Gauss's divergence theorem. It applies for the fundamental theorem of line integrals. It applies for Stokes' theorem. It applies for Green's theorem. It applies for the two-dimensional fundamental theorem of line integrals. It's all the same pattern. Right? So another really good little learning opportunity. Okay. So, moving along. Examples. I've got 6 examples here. Again, these are kind of supplementary, and we do have a lot to do, and tough choices and all that. So I'm going to focus on what I think is really the important part of these 6 examples. By the way, in past semesters, time has been even tighter, and I haven't even had time to do these 6 examples. Related to that, let me also mention, in those past semesters when I haven't had time to do these at all, I've recorded detailed discussions and put them up on my YouTube channel. And so what I'm going to do is I'm going to take those recordings from the past semester, I'm going to upload them to our playlist this semester. So if you want to see the detailed, the full, all the dirty little details, right, then you can refer to those at your leisure. So anyway. So the big idea, again, the fact that these are examples, my goal here is not to teach you how to compute a line integral. My goal here is to teach you how to use the diagram to identify the best method for computing the line integral. Right? This is about diagnosis, right? Not plug and chug. So here's what I claim is the way you're going to make use of the diagram. Figure out where you are first. Where on which diagram does the question apply? Once you know where you are, do what the diagram says. Compute the appropriate operator. Compute the appropriate boundary, as the diagram will basically tell you to. Do what it tells you to do, and then figure out what that helps you understand. What can you conclude from what the diagram has instructed you to do? Right? And then pick your best method. And by the way, always keep your head on a swivel. I mean, there's wonderful bits of good fortune that show up now and then. Sometimes you get lucky and the resulting integral will have a symmetry. Sometimes there's a geometric coincidence that works out really helpfully. Always heads up. Sure, right? But pick your easiest method and off you go. Okay, so let's see this in action. Here we have a vector field, and we're supposed to compute a vector line integral. Okay, slow down. Notice our vector field has 3 coordinates. That means we're in 3 dimensions. This is not a 2-dimensional problem. Right, it's a 3-dimensional problem. Ditto, the curve, given parameterized already, has 3 coordinates. We are in 3 dimensions, and in 3 dimensions, we're being asked to compute a line integral. Okay, so to the diagram, we're in 3 dimensions. The R2 diagram doesn't have anything to do with it. Right? So don't make that mistake. Don't be in the wrong sort of world. here we are in 3 dimensions. We've been asked to compute a line integral, so this is where we are. That's our context. Okay, what does the diagram tell us to do? What the diagram tells us to do, it seems, is to take our integrand vector field. Well, that vector field, the diagram is telling us to compute the curl of it. Now, why are we going to compute the curl? What are we going to do with the curl? To be determined, right? We'll find out when we get there. But it's going to be useful one way or the other, compute the curl. By the way, here's another thing the diagram tells us. Don't compute the divergence. Right? What would the divergence have to do with this? The divergence doesn't have anything to do with computing a line integral. Right? So not only would this be a waste of your time, this would be what I'm going to call a bad look. Right? You got to keep in mind as you're grading, what you're trying to do is trying to impress the grader with how much you understand. Right? And shotgun style problem solving is not a good look. Right? It makes it, we can tell. Right? So, if you're throwing everything you can think of at the page in the hope that something will stick, again, we know that move and we know what that means. So if you have on the page that you're computing the divergence, it makes it look like you think divergence somehow connects to a line integral, and it doesn't. Right? So not only need you not, you should not compute that divergence. Does everybody see the point there? Right? So this will prevent you from making choices that again the grader might think poorly of. And we don't want to make our graders unhappy. By the way, keep in mind on the final exam, it's a course-wide final exam, right? And it's graded by committee. People are going to be grading your final exam that are not directly associated with our section of the course. So keep that in mind. Okay. All right, no divergence, no triple integrals, likewise. Triple integral, no way, no possibility. No divergence theorem. Keep all of this off your page when you're interested in computing a line integral. Okay, so we're going to compute the curl. By the way, we're subsequently going to take our, subsequently going to take the curve that is our domain, and we're going to look at the boundary points because the diagram tells us to. We'll do that also. Okay, so off we go. I'll just highlight that again. Off we go, and by the way, I'll save us the trouble. Make sure you know how to compute curl. Again, this is not plug and chug time. This is diagnosis time, so let me just cut to the quick. When you compute the curl of this vector field, you will get 0. Make sure you can do that, of course. Well, what does that tell us? It tells us, because we had a vector field of which we computed the curl and we got 0, that tells us there is an anti-gradient. That tells us that the fundamental theorem of line integrals is on the table, and we have identified, by the way, following the instructions of the diagram, just doing what we were told, right, and understanding the basic patterns in the diagram, we have identified a good way to solve the problem. Does everybody see how that worked out? Okay, cool. Now, while we're at it, let's also do the other thing. Let's look at this curve and, let's see here. You know what I'm going to do? I don't want to erase it, but I wanted to use green for something else. Let's look at what's the nature of this curve. And again, our curve is parameterized like this. So our curve is something like so. And if you put in t equals 0, you'll get the starting point. And if you put your ending t equals 1, you get your ending point. And what you will find, if you plug those in, is that the starting point and the ending point are not the same point. This curve starts and ends at different points. Now, what does that tell us? That tells us our curve looks like this. It does not look like that. if the curve doesn't close up like so, how could it be a boundary of anything? Curves that don't close, not boundaries, right? If you have a fence that starts and ends at different places, you can't keep any sheep inside of that fence. There is no inside of the fence. Does that make sense? Right. So, back to the diagram. What does it tell us? We took our domain curve. We computed the boundary. We found that the boundary points are not the same. Said differently, there is a boundary. This is not one of those, this is not a closed loop that never starts and never ends, right? This has a boundary. So therefore it can't be a boundary of any surface. That means Stokes' theorem can't apply here. Stokes' theorem is only for boundaries. So not only have we identified what theorem we can use, we have also identified, following the instructions of the diagram, I'm just doing what I'm told here. We have concluded what we can't use and therefore should not waste our time with. Is that all right? Okay. All right, so again, now my big sales pitch today is, golly, isn't that handy? Right? All you got to do is take all of the, bazillions of ideas that we've talked about in this course and just organize them in your mind by way of the diagram and the patterns and the tips and tricks and the shortcuts that just fall into your lap. Right? So I am a tremendous fan, that's probably obvious, of thinking about things this way. I think this diagram should be in every multivariable calculus textbook, and it's not in any of them. So weird, right? Very, very powerful. Okay. All right, so the rest is details. Y'all know how to do the fundamental theorem. We've done examples of that. If you want to finish out the details of this, cool. Go ahead. Okay, next example. Again, 3 dimensions. Again, line integral. Same context. Again, we're here. Again, we're going to compute the curl as instructed. Again, we're going to look at the boundary points as instructed. And what you will find is that the curl is 0. Let's see here. Yeah. You take the curl and you will get 0. Make sure you can do that. Right? The partial derivatives end up all being 0 in this case, actually. Pretty clear once you see it. And then you look at the endpoints, and it's going to turn out that the starting point, r of 0, will actually equal to the ending point, r of 1, in this case. So you might say this curve, because it starts and then ends at the same point, it doesn't really have a boundary. It depends on how you want to say it. The boundary is nothing, whatever. You can keep sheep in this pen. Suit yourself. And so I can conclude 2 things from this. First of all, this tells me there's an anti-gradient. This tells me there's an anti-boundary, I like to call them. There is a surface whose boundary is this curve. So back to the diagram. I got 0 there. I got 0 there. I know there's an anti-gradient. Fundamental theorem's on the table. I know that there's an anti-boundary. Stokes' theorem is on the table, and we've got options. And by the way, you can use either option in this case. Whichever method you want to use to crank this out, you want to use the fundamental theorem, works out great. You want to use Stokes' curl theorem, fine and dandy. Take your pick. By the way, they will both give you 0. In fact, now I'm not going to make this a theorem because I don't want to prove it. It's this is too narrow to want to go to the trouble to make it a theorem. So you can't cite the following on the exam, but just between y'all and me, when it happens that both theorems apply, you will always get 0. And the reason, if both theorems apply, there can't be boundary points. Or said differently, they start and end at the same point, which means you are subtracting whatever f of the starting point is, whatever f of the ending point is, they have to be the same thing. They are the same point. And so you're subtracting something from itself, and you will get 0. Or, if you prefer, again, in a situation where both theorems apply, then the curl has to be 0, which means your integrand for this surface integral is 0. You're integrating 0, and you will get 0. Right, so that is kind of nice that there's this little convenient little thing to keep in mind. Again, you can't cite this as a result. You do have to show me one computation or the other, but nice to know what the right answer is while you're doing it. Okay, everybody happy? Wrong button. Moving along. Again, 3 dimensions. Again, line integral. Same context, same instructions. Let's do it again. This time, the curl. Make sure you can do this. Is not 0. And what do we conclude from that? Right? We've got, let me clean up the mess. Oh gosh. Just get rid of. Okay, so I computed the curl. I did not get 0. That means there is no antigradient. That means the fundamental theorem is off the table. Forget about it. Won't work. No chance. Don't try. Again, two negative side effects of trying, when in fact you should know that it would never work. One is it wastes your time. The second is bad luck. Right? So again, try to impress those graders. So no point in even bothering with antigradients or fundamental theorem. On the other hand, wrong tab. Here we go. What can we say about our curve? Our curve here is an intersection of a plane. Again, rescue my colors. A plane with a cylinder. And so, if you draw that, here's the cylinder, and you think about how does a plane intersect with that. That intersection, our curve, is going to be an ellipse, sort of like so. And we'll worry about the orientation when cross that bridge when we get to it. Everybody good so far? By the way, here I don't need the diagram to help me out. Is that curve a boundary of a surface? Well, of course it is. I can see it right there. Boom, there it is. Yeah, that curve is a boundary of a surface. So Stokes' theorem is going to be our lead option. Right? We did not get curl to be 0. There is no antigradient. Thank you, diagram. And so fundamental theorem's out. Stokes' theorem, in this case, is in. Okay. Now, it turns out Stokes' theorem is not particularly helpful here. It applies. It's an option. You can do it. It's no problem. But what you end up with just ends up being not so great. You end up with a flux of curl, which we just computed, dot, I'm going to say little n ds. And, oh, hey, cool, I can understand that little n, because the little n is a normal vector to our surface. Our surface, I see, our surface is right here. Perpendicular to that surface is perpendicular to this plane, and I can see what's perpendicular to that plane very easily. 1, 1, 1. Wait a second, I need it to be a normal vector, though. Excuse me, a unit vector. So 1, 1, 1 over square root of 3. Ooh, by the way, don't forget plus or minus, because we haven't thought about orientations yet. And here's the thing, right off the bat then, you look at how this is starting to play out, and the dot product is not 0, but it is a constant. That's nice. Constants I can factor out, and what I'm going to be left with is I'm going to need to know the area of that solid ellipse. And how do we compute the area of a solid ellipse? Well, I have to parameterize, and I got to go through that whole tedious song and dance. Right? So what's happened here is I had a plug and chug situation, and I have successfully used the diagram and Stokes' theorem as a result, and I have turned it into a different plug and chug situation, and I'm not at all clear that it's better. Right? In fact, I think it's probably not quite as good. I think in this case, your best move is to just parameterize the original curve and do it that way. So, this is what you might call the confession aspect of things. As much as I love these accumulation theorems, and yes, they are bonkers useful in many, many situations. They are tools, not wands. Sometimes they're not that helpful. So, yeah, keep that in mind. Is everybody okay with this example? Okay. All right. Now this is a very similar example. Very similar. Again with the 3 dimensions. Again with the line integral. Again with the you got to compute the curl, blah, blah. Oh my gosh, in fact, again with the exact same vector field. Right? And again with we have a cylinder intersecting a plane. The only difference here being that it's a different plane. Everything else is exactly the same. So, if it's pretty much the same, why would I have a different solution? And the reason why is the details work out different. When you apply Stokes' theorem, right, you compute the curl. Still that. You look at the normal vector. Still this. We'll figure out the orientation if, cross that bridge when we get to it. That normal vector is still, though, like so, plus or minus. And still, it would appear that we're computing wait a second. Wrong normal vector. Okay. Sloppy me. Sloppy. It's not this because we've got a different plane. While we're looking at this as it is, you can see why we'd be pessimistic. We're going to have a constant integrated over a solid ellipse. We're going to need to compute the area of that solid ellipse. We're going to have to parameterize. Doesn't seem like it's going to be a win. The win comes about from the fact that this has a different normal vector. Again, easy to write down. Again, don't forget your plus and minus. Normal vector is pretty obviously 1, 0, -1 over the square root of 2. And now this dot product is 0, and we walk away. So even though these two examples, right, you look at this example here, Stokes' theorem wasn't useful at all, really. It applies, but it just doesn't help us. Very, very, very similar example here, and it applies and turns the computation into awesome convenient. So that's, again, tools, not wands, and sometimes tools work. How we doing? Everybody all right? So you gotta look through the details and figure out what you can. Okay. Next example. This is kind of a cool one. Still 3 dimensions. This time, though, we're computing a flux. So everything changes in the diagram. Totally different context. We are now over here looking at flux. 3 dimensions, of course. And totally different instructions then. Don't compute the curl. Our vector field is here. We're supposed to compute the divergence of it. It wouldn't make any sense to compute the curl of this vector field we're given, like it's the integrand of a line integral or something. It wouldn't make any sense. Don't waste your time, and don't adopt the bad look, right? Counterproductive. Right? So again, the diagram is going to keep you on track and keep you looking like you know what you're doing, right? So valuable thing. So we're going to compute the divergence. We're then also going to look at our surface and think about what its boundary curve is, because who knows, that might be useful. Okay. So, we compute the divergence. And let's see, x partial, y partial, z partial, we get 0. So, nice. By the way, we didn't even have to compute the divergence. The divergence was obvious because it says right here that F is a curl. The divergence of a curl is always 0. And so that's kind of a nice little freebie. But anyway, take a pick. So not only does the diagram then allow me to conclude there is an anti-curl, in fact, the other givens of the question, because I got 0 here, the other givens of the question tell me what this anti-curl is. The thing whose curl is the F that I was given, here it is. The thing whose curl is the F I was given. So you got the anti-curl. Now, it had to be, I can't tell you to compute the anti-curl because we don't know how to do that, right? It turns out it's actually not particularly easy. But in this case, I kind of subtly gave you the anti-curl. How are we doing? Everybody okay? So if you want, one way to solve this problem is to say, well, we've got this surface. Okay, we've been asked to compute. Flux through that surface, but there's an anti-curl. So instead of computing a flux, I can do a line integral of that anti-curl. So I can instead look at the boundary, think about orientations, blah, 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 and I can do a line integral over this curve of that anti-curl 0, 0, XYZ. And so Stokes' theorem tells us I can compute this flux with that line integral. Now the question again always arises, is this helpful? Is this a good thing? Let's see, is it a good thing? Actually, it's a really good thing because, check it out, our dr vector here, as I move along that curve, that dr vector is always horizontal. So that dr vector, in other words, dx, dy, dz, well, it's horizontal, so that dz is 0. And that dot product, therefore, obviously 0. Game over, we win. How we doing? Everybody all right with that? Notice I'm just doing what the diagram tells me to do, right? I'm just following orders, right, as it were. Okay, here's another way to solve this problem. By the way, this is perfectly good, full credit, awesome. Don't think we can beat it. Very nice solution. There's another solution, though, that's also very good. And it is, let's see, I'm going to take forever if I do that. Also comes out of the fact that the divergence is 0. So what else do we know about vector fields where the divergence is 0? And again, diagram. If you have a vector field where the divergence is 0, we know that it is surface independent. And so if we want to apply surface independence, also on the table, go ahead. Surface independence, totally fine. So back to the question, again, our surface that we were given is this. The boundary of the surface is something like this. So there's our surface S. Here's the boundary of S. Surface independence tells us I can pick any other surface I like. No surprise, I'm going to pick that nice flat solid ellipse in the XY plane as my new surface. It's got the right boundary. We play with orientations if and when they come up. But Fooey on S, let's compute the flux through that blue surface. And the nice thing about that, when I say flux, wrong thing. When I say flux through S is flux through, I'll call it E for ellipse down here. it's still the same vector field F. But I've got a new surface, which means I've got a new normal vector, plus or minus. Again, we'll worry about orientations if we need to. There's our new normal vector. Our new normal vector is, again with the plus or minus, 0, 0, 1. And again, the dot product 0. Poof, game over, we win. So another perfectly fine way to do it. You can do the apply Stokes' theorem and works out great. Or in this case, you can also apply surface independence, and it also works out great. Okay, all right. Okay, let's see here. Last one, and then we're going to do some chapter 4 stuff. All right, let's see here. 3 dimensions, computing a flux. Same context then, right? This is where we're at. We're going to compute the divergence. We're going to think about the boundary of our surface. Let's just see what happens. Let's see what's on the table. Let's see here. You compute the divergence. Again, make sure you can do this. Divergence is 1, which is not 0. And that takes a bunch of stuff off the table. Surface independence, for example, out of the question. This is not surface independent. Don't even try. It doesn't apply. No surface independence. No anti-curl. Also, right? No divergence is not 0. There is no anti-curl. Stokes' theorem is off the table. And again, bad look, right? So there's an opportunity to make your grader happy and impressed just from realizing that divergence non-zero means that this is not an option. Okay? All right. Okay, so the next thing, we're going to look at the boundary curve of our surface. And, let's see here. What is our surface? Our surface is a sphere. What's the boundary curve of that sphere? There is none, right? Or you might say 0. But there is no boundary. And so because the boundary is 0, and again, geometric appeal, right? There's no boundary curve. And that is ultimately, because the surface has closed up, the act of making that boundary disappear by the surface closing up also means that it becomes itself the boundary of a solid. It's the boundary of the ball. So because the boundary curve is nothing, we have an anti-boundary. And Gauss's divergence theorem is on the table. And that's the way to do this one. For sure. Everybody good? Okay. All right. Okay, so let me say a few words about chapter 4, and then we'll. I'm going to give you all 5 minutes in 2 minutes. I'm going to give you all 5 minutes to do course evals. This is course eval day, because we got the exam coming up on Tuesday. So chapter 4 is actually a lot of plug and chug. It's a lot of follow the instruction. Section 4.1, there's really very little to say. There is this idea that I'm sure you all remember from long ago called Taylor polynomials, and there's a formula for it. And it basically, a Taylor polynomial is just a way to mimic a function with a polynomial. Well, you can do the same thing for multivariable functions. And you can find that this formula right here, it's a little clunky, right? But that formula right there is what we call the second order Taylor polynomial, and that mimics the function in the same sense. It's got all the same values and derivatives up to and including the second derivatives. Just make sure to know this formula. The one little issue is this matrix, the thing that is the matrix in this second order term, which by the way you'll recognize as a quadratic form. Right? Y'all may have thought you were done with quadratic forms when you got out of Math219. But they're in 218 because they come up elsewhere, such as here. So that matrix, you just got to know what it is. It's called the Hessian matrix. It's made up of the second order partials, organized in the obvious way. And plug and chug. So that's section 4.1. And let's see here. I guess that's a pretty natural place to pause and let y'all do course evals. We will talk about 4.2 and 4.3 on Tuesday. It's been good having you in the class. I mean, we're kind of down to the end here. See you on Tuesday for the exam. See you later.